Okay, good evening. So basically this is a video I'm doing to compare the first table where I got the channel efficiency before I'll go to the next one and explain every table that is found in the work. So on the first table here, where we are having a frame length, time, slot interval and channel efficiency for a frequency query algorithm. Now I use Silver's work, okay, Silver, Israel and Carlos work to compare this. So as you can see, this is Silver's work, and they are using a bit size of 2 to 10, 2 to 10, and basically the auto of this particular work is using an inverse type of solution. They are using the solution based on inverse. It is actually an inverse. That's the reason why you see here they said if n does not match the optimal interval, the frame length will be adjusted to find the appropriate size based on the backload calculated as follows. Now this is actually the formula for calculating the optimal interval if this particular n does not match the optimal interval. That means it does not match anything here, maybe within this range, within this particular range, within this range, because the system is categorized based on its bits. I told you, when a card is registered on the system, we look at the range, just like when you convert maybe 0 1 in binary digit. You know, 1 actually in binary digit is 1. You understand? So basically, if you convert 1 and you add up maybe 7 zeros in front of it, it will make it 8 bits, so that it will not give you 1 byte. Now those zeros you add in front, they don't have any influence on the number. Actually, they don't have any influence on the number. The only thing is, when there's always a 1, that means there's always an on, the system is going to respond to that particular query. So what they did here is that from 1 to 5 they sample it under the binary digit 2, then from 6 to 11 they sample it under the binary digit 4, and for you to find your frame size, you are going to multiply this value here by 2. So you understand, that means 2 raised to the power of any value you get at this point. 2 raised to the power of 2 is 4, 2 raised to the power of 3 is 8, 2 raised to the power of 4 is 16. While for you to calculate the channel efficiency, since they are using actually an inverse solution to calculate this, because what the person is trying to calculate at this point is that he is just making a calculation that n will not match the optimal interval. So that is what we are saying here. Here his own, what he's doing is that n, that is the number of tag, the tag n will never match the optimal interval. That's the reason why he used this particular formula to solve the backload. Then if you want to calculate the efficiency of the channels, you're going to use this particular formula which he provided. So once you substitute the values into the formula, you're going to get each of these values one by one, like this, the same way. So same thing also in our own work here. Our own will not use inverse, because we know that basically there must be a tag. Since all of us are going to register the tag, there must be a tag that will correspond to an interval. Each of our tag there won't be anybody that was going to come with any card outside the stipulated card that was divided or was shared from the institution. So each and every one of them will have a card the range, within the range, within the interval. That's what I mean, within the optimal interval. So nobody is going to come with any card that is not within this range. And here we are sampling actually from 4 bits. So as you can see here, they sample from 2. So but we skip the whole of this point. We started our sampling from 4 bits to 9 bits. Okay, so we sample from 4 bits to 9 bits, and if you follow the same format, the same formula, our frame length here, we call it frame length, but in Silver's work he call it frame size. So but here we call it frame length because our own formula too is actually different. We are not using an inverse notation. I hope you understand. So we are not using an inverse notation. That's the reason why we have 2 raised to the power of our bit rate is going to give us our frame length. And if you look up here, there's a place we stated that also. We said our bit load is equal to bit rate all over frame length. Now this bit load, according to Silver, it is actually the backlog, but we don't calculate, we are not calculating backlog because we are not going to work with inverse. That's the reason why you're getting 1 here. There's a 1 here, which is an inverse of the whole thing that is supposed to be here, an inverse of that particular thing. But yeah, we are not using inverse. We are going on a calculation or a solution that every tag must be within this particular interval. Each and every tag is going to be within the interval. There won't be any tag that is outside the interval of this 12, ranging from 12 to 711. All of these tags, all of the tags from our systems are going to be within this range. So how do we then calculate our own efficiency now? In order for us to calculate our efficiency, we are going to say, okay, bit load is equal to bit rate all over frame length. Now, what is our bit rate? Our bit rate, the first one is 4. If our first bit rate is 4, then what is our frame length for the same bit load? It is 16. So you divide this by 16 and you have 0.25. So once you get 0.25, you will now substitute this into the main formula, and our main formula for channel efficiency here that we use based on our own work is actually this. As you can see, tag, which is nq2 minus nq1, as n for the tag bit load 1, 2 minus the interval 1, interval 2 minus interval 1, all over our frame length L, which is 2 raised to the power of what? Our bit rate. Now minus bit load. Now if you look at their own here, what Silver did here was that he said, in order for you to calculate our efficiency here, our efficiency for each of these bit rates is equal to 1 all over the final tag minus the initial tag plus 1. That means this interval 2 minus interval 1 plus 1. Then it will now give you your solution, or you can actually solve it as summation of what? N is equal to interval 1, and our interval 1 is also going to give you n over 2 raised to the power of q, multiplied by an inverse, which is 1 minus 1 all over 2 raised to the power of q, and our 2 raised to the power of q is actually our frame size. Then everything raised to the power of n minus 1, and our n is actually our tag. So you're going to take the value n here as For the first instance here, n is equal to 5. So 5 is going to be here, 5 minus 1, you write it, then 2 raised to the power of q. In our first instance here is 4. So you write 4 here, and that would make it 1 minus 1 all over 4 close bracket raised to the power of 5 minus 1. I hope you understand. So you now also substitute here. Also here is going to be 5, and this is going to be 4 multiplied by what you get here, and that is how he came up with the solution for the inverse notation. But we are not using inverse in our own, because no matter what, we know that all our tasks are going to be within the optimal intervals. So all of them, they are going to be in between these numbers. None of them will be outside this. All of them must be within this number. If there's any cut or any task that is brought to the system, because what we are trying to see is how our system is going to be more effective in controlling um, collision. So we want to see how our system is going to be more effective in controlling that. So that was why we did not imagine anybody is going to come with any tag outside the interval that has been given. That's why I said we are comparing this table for frame length, time slot interval, and channel efficiency for a frequency query allower. So you see we captured the interval as well as the frame length, then also the channel efficiency. So we are not imagining that there will be something outside this particular interval, just like Silver did his own. He said, okay, let us say if n does not match the optimal interval, but our n matches the optimal interval. So our reader is going to actually work. Now, if you scroll down again, you get to this particular point where we have an identification process in query tree alpha algorithm. Now let us go down also. Now if you look at this particular table, this is the identification time for different time slot types. Now this is actually for Silver. Silver use an interval, so, and he also use time frame to make his own analysis, his findings, and also provide solution to the collision. So here what Silver is going to do is that what he did, or what he actually did here, is that he knows what he's working on. What he's working on is actually an inverse solution. So basically, if he's going to work on an inverse solution, he's going to provide all the parentheses, all the parameters, all the things that are required for him to convert the equations back to its normal size, back to the value that you're going to actually see here, because what he's using actually is an inverse. So basically here he's not using a bit or a query tree. Here he's not using a query tree to compare this particular slot type. So that's more reason why we do not compare our work using this. And if you look at our own work, we are using what? We are using a query tree allow algorithm. So at this point we did not use this particular one to test for our query tree. I hope you understand. So you can see some graphs based on inverse. So we didn't use this. So I'm going to open the table we use and compare our query tree allow algorithm. So coming to the second table, which is table 1.2, identification process in query tree allow algorithm. Now here there's one thing I want you to understand with this particular table. This table, we are using binary digit to compare all the data that are required, And mind you, query tree algorithm, according to this particular work here that we are comparing to it, because we want to make sure that what this particular author is doing is not the same thing with our own, but we are going to compare the mechanism at which the other person is using and our own, and see which one is actually the best. Okay, so here the query tree algorithm actually is just for us to have a prefix that will be added to our frame size. Okay, so basically the query tree is not as if it's going to have maybe a serious effect in our program, but the only thing is that the query tree is actually responsible for the prefix of every tag that will be transmitted on the system. I hope you understand that. And actually a reader is going to send a prefix and also a frame size together, not as if it is going to send a prefix differently, then also send frame size differently. So it means this particular table, this table, and the other table here, where we are having our frame length, we are calling it frame length here, but other authors are calling it frame size. So frame length and frame size are still the same thing. I hope you understand. So this frame length, which is 16, 32, 64, 128, 256, 512, that we use as an example, and also as the only tag that we are going to be creating for the system actually, because we want to create all tags within this particular range or interval, as you can see. So there will be, the system is going to pick up each of them, each of these frame lengths, and also pick an interval here, which is actually going to be like, okay, the query interval, and the query interval is going to be in bits, which is zeros and one. So for example, now let me give you an instance with this work, or let me give you an instance with the one I compared before I will explain our own. Now looking at this particular table by JD, this table actually, this is the query. JD call it query, while we call it query interval. I hope you understand. So they are the same thing. Query interval, query is still the same thing. Okay. So here at this particular JD's work query here, when the system collects a prefix of 0, it will also collect a frame size 4. Now mind you, the reason why we are having collision here, is because the prefix here is not constant. Like, it's still, maybe now this card you're using, the prefix is 0. Tomorrow you come and try to load it again, it's showing another different thing. So this thing is not stable. The query is not stable. That's the reason why once this particular prefix is 0, it means it is not identifying the prefix at which the card was programmed with. Maybe someone tampered with the card, or there's an issue with the system or something. The reader was unable to identify it. So that is the reason why we are having 0 here, and the frame size actually for that particular card is 4. So since the system is unable to identify that card, so the query is going to be 0, and the frame size is actually 4 for the first instance. Remember I told you the Otto here, and also Silva and Israel, all of them started from 2. They use 2, 3, 4, 5, like that, That's the interval, the query interval that they use. But our own work, we are starting from 16. That is why our own frame length is different from their own frame length, even though they also capture some of our own frame length also. But our own frame length, we started from the the best bits. Actually, we want to use the best mode of transmission. We want to see how we're going to reduce collision on the system drastically, so that our system can handle any situation that will occur with any tag, so that we don't want a lot of complaint on the system that are unable to respond, unable to identify card, or there's collision, stuff like that. So here the query is 0, and our frame size is 4. So this is actually the prefix, And the prefix means that particular card that was displayed on the system for the card reader to read, it was unable to identify what type of card is that. But basically the card is actually having a frame size of 4. So here they're calling it frame size, and the frame size is actually 4, but the prefix is not identified. And the alloa algorithm that is responsible for identifying this is actually the query tree alloa algorithm. So if you come back to our own work also here, instead of us writing 16, 32, 64, we now converted each of them to an equivalent bit. Those numbers you're seeing here as bit length is actually the frame length. So, but we converted each of them to binary digit to make our own table unique and also different from other authors, so that it not be as if all of us are doing the same thing. Because mind you, number one, we are not using an inverse notation. We are not calculating, maybe we are saying n must not be among the interval. So our own n is among the interval, that is tag. Every tag must be within the interval. All of them must be within the optimal interval. All of them, all of our cards must be captured, and all of them are going to be within the optimal interval to avoid collision. Our own is to see how our system is going to avoid collision to the minimal level. So that is the reason why we don't want to actually use an inverse notation. So here I also gave the calculation how we actually got these numbers, because these numbers are actually our frame length, but we converted them back to bit length. Now if you look at JD's work here, his frame size here, he actually added them as normal numbers, that's normal integer numbers, as you can see from this point here. Let me show you where he got them. As you can see here, this is actually a converted code in binary digit. So the other work is actually above, so I'll show you in our own work. Look at the frame length here. Now if you look at this frame size here is 16, 32, 64, 128 and 256. That is where JD stopped. He did his own using Epoch size, and he also compared it using Epoch size. Now he used 16 frame length or frame size to 256, while our own work we use 16 to 512. So everybody have their own opinion to add which length will they use and stop. So back to this particular work here. Now the frame size here he used 4 4 4 4 2 2 2. So he now divided his own work into 2. He divided his own work into 2. So if you go back to our own work now, below here, below the table, you are going to see that okay, 16 in base 10 is equal to this, 32 in base 10 is equal to this, which is in base 2. So this one, 16 in base 2, 16 in base 2, in base 2, in base 2, in base 2, all of them in base 2. So 16 in base 2 is equal to this. Now if here we are having this, that means it's going to be 16 here, and here also we are going to have 32. This place we are going to have 64, and here we are going to have 128. Same thing here, we are going to have 256, and finally we are going to have 512. So that is it. Now with this number that I've added, it means when our query was entered, that's the first tag was presented on the system for the card reader to read. Now there was an issue here. The prefix was not identified. That's why we are having this 0. The prefix was not identified. And our frame length or frame size, anyhow you want to call it, the frame length, frame size, all are the same thing, length and size all. So our frame length is 16 at this point for that particular card. So if it is 16, it means it is 16-bit. Now, but the prefix was not identified because both the prefix and the frame length are going to be captured together in the system. They are going to be captured together. Now, the frequency allower, which is this table above, this particular table, frequency query allower, is responsible for providing the frame length. While this query tree allow algorithm is responsible for providing the prefix that will now be added to the frame length for that particular tag to be read successfully in the system. Now, and here now, our own query did not identify the frame, did not identify the prefix of that particular card, so it is 0, and that's the reason why we are having collision, and the status is also unsuccessful. But once our query was identified, here you can see 1 means identified. Now since it is identified, there is what, at a frame size or frame length of 32, then there was success in transmission of that particular tag. It was successful, the tag was identified, and that means there was access to the system. Access was granted to the system at this point here. Meanwhile, here we are having 0, 0. There is 2 particular cards presented, and each of them, their tag prefix was not identified. And since they are not identified and all of them were presented at the same time, so we have no response for them. That means all of them are unsuccessful. Once your card has not been captured, automatically it will not respond, and if it do not respond, then there's no way you will be given access. And all of them were found at this particular frame size 64. They have both 64 bit length, or you can call it frame size or frame length, anyhow you want to call it. That's right. Now here we have a collision because the first instant the card was not given, the prefix was not given, then prefix given again. So there's a collision because the card is either it is someone's card again, because the system was trying to identify one card at this particular frame size, frame length 128. Then there was a card that was presented, another card was also presented, so one doesn't have the prefix, another one was having the prefix. So automatically, in order for the system not to confuse and give access to the wrong card, there must be a collision here. So all of them will not be given access to the system. All of them will not be given access to the system. So it is going to be unsuccessful. While at this point there was a card that was presented. Now this card was presented and automatically the prefix was not there. Then another card was presented, the prefix was there. Another one was presented, the prefix was not there. So this card that was presented secondly, it will be given the access because it understood that, okay, at the first instance this particular card was presented, so no prefix, and that person now brought his own card and put there was prefix. Then you now still took the first card again and presented to the system. Now the system is sure that, okay, no, I'm giving access to the middle card, not actually this first card, because the first card was presented twice. That's the reason why you're seeing this 010. The card was presented twice. at this point and also at this point. So we have access given to this particular card. Meanwhile, the last one here, there was a card that was presented 3 again. One was invalid. Now you brought the second one and tested, there was access. Okay, it identified the prefix. Then again, the system was trying to like, okay, if I leave it at this point, there will be collision. So if there's collision here, that means none of them will be given access. None of them will be given access. So you still presented the second card again, and at this point you presented all of them are still granted access. It means yes, access was given to the second card, not the first card. So that is why you have success here, and it is identified. That is actually what this table is doing. Now if you look at its own, it's still the same thing here. So you can still continue from there and check. Now if you come back to this particular table, which is the last one where we did our comparison, now we compare this table using this particular table. Even though most of the authors couldn't provide solution, they couldn't provide formula that they used to calculate their table, but as an expert in comparison of this particular Aloha algorithm and so on, I discovered that okay, each of them are having the same frame size. Okay, let me see if I have another person's work also so that you will see it. Let me see this. Okay, this one is still the same thing with this one. Okay, let me open this and see. Okay, silver. I think most of the other authors are having it online. So but these are the ones I downloaded. So but let's continue from here. So in our work, if you can see here, this is actually the these are the variables we are using to compare the this thing, the table with. That's our performance comparison using Epoch size, okay, which is ES. Now we are using C0, C1 and CK. From our work here, we are having C0, C1 and CK. Where did we got all these things? We got them from this particular table, our query tree. Here we use collision, we use identified, we use no response. Now if you look at it, no response is C0, identification C1, which is identified, then collision, which is CK, and this is comparison based on 3 results. Now how did I know that we are going to have 3 results? There was a place, if you read, I think above, there was a place here that I said our table, we are going to divide it by 3. Okay, yes, and that is the case. Now here we said the first case is at 16 to 32. So this is not the division of the case. Our first case is going to be this 16 to 32 here. So every tag that is within the range of 12 to 44 are going to fall under our first case. Now close to, I think close to about 50, an ideal epoch size, that's an ideal epoch size, close to 50, but it's not 50. So you can see 44 is actually close to 50. You just need only 6, it will make it 50. Now the case demonstrate the best performance as we expect to see in table 1.3 below, and this is the table. Now, this particular case from 16 to 32 is actually going to be our base. It's going to be the best solution to the algorithm, because each of them, if you look at it, if you look at the collision level here, it's almost close to the identification stage. That means the system tried its possible best to find solution to that particular collision, but it's just that there are some technicalities that need to be handled. That's the reason why the number is close to the identified, and the identified is actually 100%. So this one is like, this is constant. Once a system is identified, it is 100. There's no any addition or subtraction. So once it is 100, it is identified completely. Just like I would say, if you get 100 over 100, meaning you are completely good in that particular course or that particular thing you're doing. So this is actually 100. We don't argue this one. That's why even the other person got it 100 complete. 100. You cannot change this particular value. You can't change this value. This value is constant. You can't change it. So at this particular point of our first case, there's a formula I wrote, because if you look at most of these authors, they don't want people to actually copy their work, and they don't want people to get solutions to some of this stuff without contacting them. So here in our own work, I gave out a formula that we use to calculate our C naught and CK. So as you can see here, in order for us to calculate our no response, which is C naught, no response C naught is equal to tax. That's the final minus the initial. This particular one is the final, and this one is the initial, all over our frame length, which is 2 raised to the power of q. Then multiply by C1. Multiply by C1, because what we are trying to get is 100%. This place should be 100, this should be 100, and this one should be 100. 100, 100, 100. But since we cannot get 100 here, we cannot get 100 here, then it means if it is above 100, there's collision, and if it is below 100, it means there's no response, because it's not up to our expectation, so no response. But if it is above 100, that means there's a collision here. There's a collision. There's a collision. So here, our no response, we are calculating it now. For example, if we say when Q is equal to 4, which is our bit rate, is equal to 4, no response will be equal to 22 minus 12 divided by 16 multiplied by 100, which is equal to 10 over 16 times 100. And this is where we now go the first instant of our no response, 62.5. Now for us to also calculate the collision here, there's a formula for it. Our collision is going to be what? Frame length, which is 2 raised to the power of q over the maximum query interval. Maximum query interval. Now you remember our query tree. Our query tree, I told you, it makes use of two things. It makes use of the query, which other authors call, and our own here we call it the query interval. Then it also makes use of the frame size, as other authors call it, but here we call it frame length. It's still the same thing. So here our maximum query interval is 3. How did I know that it is 3? If you go back to our bits here, if you go back to this bit, what is our maximum query interval? You count this bit, how many bits? 1, 2, 3. This is our maximum query interval. If we have other bits added, maybe 5 of them, 6, then that means our maximum query interval is 6. But here our maximum query interval is 3. That is where we got this 3 from. But these authors, other authors will not tell you where they got their own this thing from. So, but this is how we got it. Then added to what? C1. Added to C1. That is why the value before you have a collision, it must be greater than 100. So anything you calculate here plus C1 will now give you the value of your CK. So for example here, when bit rate, or you can call it Q, is equal to 4, collision CK is equal to 16 divided by 3 plus 100, and that is where we are having 105.3. That is where we got this particular value, this value. That is where we got this value. Now if you look at their own here, it's still the same thing that they got, but here one thing about it is that they calculated their no response. They calculated this is constant, then they now use this particular collision. And mind you, this particular work is based on inverse. That's inverse 1 over this, 1 over that. So this is an inverse work, because they are thinking their n, which is the tag, is not going to be registered. So if the tag is not registered, it's going to actually be an inverse of the whole thing. But based on our own, since we want to simplify the work and also make it look very unique and also handle any collision from the system, we did not use inverse. We use the appropriate way to solve it, which is without inverse. That means all our tags are going to be captured. All our tags are going to be captured. And here you can see the query, which is tag IDs. You have 1 here, 1, and the maximum is 1, 2, 3. 3 of them, 1, 2, 3. You can see. So that is how we got the whole of this. Then if you come to this query response number needed for identification per tag. Now, how did we do this one? This is actually, as you can see the key here. You can see the key as asterisk is actually no response. The square is identification, the addition is collision. So you can see this is actually the collision. This is normal identified. You can see it on a straight line going straight. This is identified. It doesn't have any issue, no arrow, no arrow. It is just straight. You can see it on a straight line going without issue. But if it is no response, it will now be below the main thing, which is our 100% here. It will now be below. That's the reason why I was explaining earlier that no response is below what? Below our identification, while collision is above our identification. And this particular graph have actually explained it for us very well, the way we're supposed to understand it. Now you can see identification is having a straight curve, a straight one, without any curve this side, that side. But you can see the no response is below the identification. That means the number is not up to 100, it is below that, while the collision started immediately above the identification. So you can see as the tag is going, we are getting larger frame length. That's how the collision also be going. It will be going, it will be going, it will be going up and up and up and up until the last tag. So as you can see, this is how the system works. So you can read this. So these are some of the comparisons, the tables we compared. While you can see their own here, what they use, you can see it here. Now their own is actually an inverse, so that's the reason why they are having this type of query response number needed for identification per tag, according to Jedong, Chen, Shangshu, Yu, and the rest of the authors on the system. So that is all about the comparison between the first table, second table, third table, and the graph itself. So everything is plotted based on how we presented our table. No presentation here that is done outside of imagination or without proof. So everything is actually here, scientifically proven with mathematical formulas. So you can still run the formulas and see if there's any value here that doesn't correspond from the formula with the example given below the formula. Thank you so much.